3, 2, 1. All right, next up is the Doppler effect. Now you've heard of this. If you ever watch weather reports, you'll hear that Doppler effect is being used for predicting weather patterns. There's also this isn't just confined to sound. This could also be involved in electromagnetic waves, which we'll talk about in just a little bit. But first of all, the Doppler effect, which is named after this guy named Doppler in Austria, who found this in 1842, is all about how the perceived frequency of a wave changes because of the motion of the push of the wave. In other words, if I'm standing still and there's a noise over there and it's not moving, there's going to be no change in the pitch. But if that object starts moving toward me, then the wave starts getting bunched together because it's being pushed into its normal sound pattern. And then as it's approaching, the frequency actually becomes higher because there's more waves coming at me over a certain same period of time. But as soon as it goes by me, it's now on the back side of that, which is now where the waves now are spread apart. And the video that I'm going to ask you to watch before I go on with the explanations on the mathematics of this is right here. And I should have gotten it into the assignment. If I didn't, then just copy this and watch this. But watch that before you go on, so you kind of visualize what's going on with that. Okay? So this is the scenario we're looking at, or kind of dovetailing into what was described in the video, and we'll have a slightly different formula, to me an easier formula than what was given. In fact, it's pretty similar to what the book used, which I think is one of the better things in the book is dealing with sound. So we're going to be issuing numbers and variables according to how I'm going to try to keep it from getting confusing, because they use S for a couple of things that so you start using capital S and lower S. I'm going to eliminate all that, make it very clear as to what goes where. All right, so there's a person driving in a car at 40 meters per second, leans on the horn. So we got these sound waves, but they're getting pushed closer and closer together. So the perception of this person is not going to be the same as the perception of the person driving the car. The person driving the car is going to hear noise emitted. Let's say the car horn is at a frequency of 200 hertz, but that is not what this person right here is going to be hearing. So it's going to be related to the speed of sound of air. So let's say that the velocity of the air here is 350 meters per second. Okay, let's say that the car is traveling, and the car is the source of the noise. So instead of using S for source like the book does, I'm going to use N for noise. And that is velocity of the car here, let's say, is 40 meters per second. Okay? Now, because we understand that from our experience and what you saw in the video, the pitch of the car is actually higher than the pitch of the car person in the car. So we're going to expect this to be higher. And so the relationship between the velocity of air and the velocity of the noise comes into play by using this formula. V sub 0, which is the frequency of the observer, is equal to the frequency of air, the frequency of the noise that's being emitted times the velocity of air over, and since we know it's going to be larger, this is something to keep in mind when you're using these formulas. If you're going to subtract values in the denominator and everything's positive, then that's actually going to make this value higher. And so what we're going to look then is the difference between the velocity of air and the velocity of the noise. How fast is it coming out of the car? Okay? So in this case, it's going to be 350 meters per second divided by, oops, forgot the frequency. initial frequency of the noise is 200 hertz. Gotta put that in. And then we'll put a 350 meters per second over the difference, 350 minus, and we said the car is going 40 meters per second. And when we calculate that out, that turns out to be 226 hertz. Okay, so this is the scenario right here. You're going to hear a higher pitch than this person here is going to hear. And then the car is going to pass. So that, that scenario then is going to be the same formula, only now the denominator, instead of subtracting, is going to be adding. So VA over VA plus VN. So that becomes 200 hertz times 350 hertz, or 350 meters per second, sorry, over 350 plus 40 meters per second. And we know that when you add in the denominator, it's going to make it the whole fraction smaller, which means the 200 hertz is going to get smaller. And indeed it does. It turned out to be 179 hertz. Okay? Now, that's one scenario. So it gets faster as it's coming towards you, and it gets slower, or it gets lower, not faster, it gets higher when it's going toward you, lower when it's going away from you. Okay? So, we take the next scenario where the sound is emanating from a stationary object. So, but it's still going to be transferring at whatever the velocity of the noise is. So that's the air. So that's, I'm sorry, let's put A for air. That's velocity in the air. Now as the car is coming toward it, it's as you can imagine now, it's going to be it's going to get scrunched up again as this is going the other direction. So it's going to be hitting those waves faster than before. So let's use 350 meters per second for that velocity of the air. Let's use the car at 40 meters per second. And the observer then in the car was not blowing the horn this time. It was just say like a civil defense horn. It's going to be the frequency of the noise, what's coming out, which again, let's say that's 200 hertz. Trying to keep the same so we can examine what new values we're going to get, and then we can compare across that. Times, and now this is going to be reversed because we're going the opposite direction. So the fraction is going to be reversed. So this is going to be 350 hertz down here. And since we know that the observer is going to hear a higher note, or higher frequency, we are going to be able to understand that the addition is going to occur on top. So we get a larger number, 350 plus 40 hertz. And when we do this, we get 223 hertz. Okay, now, if it's going away, this is toward here, this is away, so the frequency as observed by the person in the car now, instead of sitting by the side of the road, is f of n, which is 200 hertz, like I said up there, 200 hertz here. And now we're going to subtract the numerator here. So this is 350 minus 40 hertz over 350 hertz. And that's not hertz, that's meters per second. Sorry. Let's get this fixed over here too. It's meters per second. meters per second, meters per second. They all cancel out because of that, and this is going to be meters per second here, because we're dealing with velocities, meters per second. And this gives us a value of 177 hertz. So, now if we take a look at the pairs of values that we got here, we had 226 and 179, and over here, 223 and 177. There is a slight difference. Will you notice it? Probably not, because 3 hertz is not really much of a change, unless you have a really good year, which I may have one time had, but I don't right now. So, you watch particularly which form you use, depending on if you're going toward or away. This, like I said, is toward on top and away on bottom. And I probably should put that here. This is toward here, and this is away here. Okay, so your practice problems, that's the bottom of the script. You're going to be asked to come up with velocities in air that we've done before. So go back through, and if you don't remember the formula, use that. And I believe it's 331 meters per second was 0.6 times 0.6 degrees Celsius per meter per second times temperature. So, or meters per second per degree Celsius times the degree Celsius. So, if you would please, go ahead and do that. There's a number of parts to it, so I only give you 4 problems for this because there's a lot more. Have fun.